go over all of them? Alright, sounds good. Start with the first one. So, pretty much for all of these problems, there are like two equations you really want to know. And those are I know he makes his vector signs a little bit different here. Some of the squiggles on it. This is just how I do it. They mean the same thing. So you guys know this, if you look elsewhere on the equation sheet, this can be written as omega like that. So they're the same thing. That's my first question. Before I start doing these problems, do you guys feel comfortable taking the cross product of a vector? Use your hand a little. I, J, K. Okay. Yeah, it'll save you time to do vectors and matrices for cross products. So, alright, you guys are okay with that? I'll go ahead and start the problem. But yeah, those are the two most important formulas. The most important. Okay, so the first problem, 1.4, you have a bar pinned here, and then a bar pinned there, attached to a collar that's sliding along the beam. And it tells you in the problem that this angle here is 60 degrees. Alright. And you have all of these distances. Alright. It also gives you, it says one thing. It says omega AB is equal to 16 radians per second. It also says that this is constant, which means you know that the angular acceleration of bar AB is 0. Words like that, constant, those are key, those are really important. Okay. The other thing you know a few more things just because of geometry. Because of this pin joint here, you know that the velocity of A and the acceleration of A are both equal to 0. And because of this collar here, there's a constraint. D, the bar at D, it's not moving up and down. It's just not possible. So then you know that V of D in the y direction is 0, and the acceleration of D in the y direction is 0. So those are your preliminary things. Those are the things you need to know. Okay. So then we go back to those two equations that we use. And how I always like to do these problems is I start with stuff I know and I jump point to point to point. So I know stuff here, so I'm going to jump to here and then to here. Alright. So we know the velocity at A, we can solve the velocity. So the velocity at B is going to be the velocity at A, which is 0. clockwise positive. So that's another important bit of information. We're just going over review problems.
This is the first one.
Yeah, that's the first one. K cross R B respect to A. So here you have 16K cross. Now, what do you have to do with respect to A? This is just where you break it up into the X and Y. So here in the X direction you have 3 inches times the cosine of 60 degrees. And in the Y, this dimension, 3 inches times the sine 60 degrees. So we can plug those values in. Direction is also another really important thing. The reason these are both positive are because we're going from here to here, which is positive in both the Y and the X directions. If we were going here to here, they would both be negative. So you take this, you do your cross product, and you get 24 J minus 41.6 I. The other important thing, these units are in inches per second. Velocity. Don't forget units. They're really important, and if you don't include them, they'll cost you points on the exam. So just make sure to do that. Okay. So now that we've gotten the velocity of B, sorry about that.
Look.
Okay, let's try this again. So there's velocity of B. Now we can find the velocity of B. So we just use the same equation. With respect to B this time. This is along the beam. So, this we know because that's this right here. This we do not know, but this we do, and this we only know half of. So the tricky part about this part is in order to get this value, you have to do a lot more geometry. So you know the height of this, so you know that this height here, between these, is going to be 6 inches minus this, and it works out to be about 3.4 inches. And then you know the hypotenuse of this right triangle, and you know the height, and you can use your Pythagorean theorem to get this distance, which is 9.4 inches. And this is one of the reasons diagrams are really important, because you use them and you draw on them, and they give you more points. So, always draw diagrams. Okay, so using that, we can find our RDB. And BD we can expand to be BDX in the I direction and BDJ in the Y direction, or BDY in the J direction. We know BDY is 0. So then, all we have is the X component. Plus omega dB cross, and then RDB ends up being 9.4 inches in the I direction and 3.4 inches in the J direction. Okay, K cross I is J. K cross J is negative I. Alright. So now we have one equation, two unknowns. The beautiful thing about this is all the i's have to add up to 0, and all the j's have to add up to 0. I mean, they have to equal each other. So when we do that, let's take the j's first. So we end up with the j is 0, there's nothing over here, equals 24 plus 9.4 omega dB. You can solve for omega dB from that, right? Everyone feels confident? Okay, good. Pardon? Yeah, these are the, sorry, that's a very bad J. These are the J's. So if you solve this, you get omega dB equals negative 2.55 radians per second. So this bar is rotating counterclockwise. This bar is rotating clockwise. Okay. So then if we solve with the i's, we get vdx equals negative 41.6 I, or negative 41.6 plus minus 3.4 omega dB. We already know what omega dB is. We can take this value and substitute it in there. And then we get our velocity of d in the x direction. Just plug and chug. And that's going to be negative 32.9 inches per second. So you guys see how we got this far? You with me? Okay. Can I go ahead and get rid of this page? So then once we have those velocities, we move on to acceleration, because the problem is asking for the acceleration of collar D. Had it been asking for the velocity, it could have stopped right there. We got it. So the acceleration formula is almost exactly like a velocity formula. And we just go point to point to point like we did before. So you can say the acceleration at B, the acceleration at A, which we already determined was 0 because of the constraint, plus alpha A B K cross R B with respect to A. And we already determined, since the angular velocity was constant, the angular acceleration was 0. Derivative of a constant, 0. So we don't have to worry about that term either, which makes life a lot easier for us. So then, and you can use other variations of the formula. I'll go ahead and use the second one. Omega AB K cross omega AB K cross R B respect to A. Okay. So that's our formula. We already solved for this before when we solved for velocity. So when I plug in numbers, those are the numbers I'm plugging in from. Then we just cross it again. So equals, and this is going to be, we've said omega AB is 16K cross, and these are the numbers we got from before. We took that cross product. 24J minus 41.6I. Okay, and then when you do the math here, this works out to be negative 384 I minus 665.6J. And again, this is in then for the acceleration at D, we have the acceleration of B plus alpha BD cross RdB plus the same thing as before, only a different formula. So make it dBk cross RdB. Okay. I actually didn't plug and chug numbers for this one, so if someone has a calculator and wants to start plugging in stuff, that would be great. So then we have, and again, we determined that the acceleration d in the y direction was 0 because of the collar, so we only have to worry about it in the x direction. Already had RdB from last time, so that's where I'm looking at those numbers from. This will work out to 9.41 alpha GDI plus 3.4 alpha BDJ. Then plus that whole term. We end up with, we said omega BD was negative 2.55 radians per second in the k direction, cross with sorry, let's read just 9.4. Plus 3.4J. Okay. So we have this. Does anyone want to punch through these calculations? So let's go ahead and do this one first. So let's call it 24 Jason, so that's that. What's any negative? Alright. And so then when we do this cross product, we'll get K cross J is negative I, so this is positive I. 61.2I plus 22.2J. Alright, so plug that in here, rearrange a little bit. All the J's, maybe 665.6 plus 3.4 alpha BD minus 22.2. Alright, j plus that. So you take the i's. Yeah. That was here. So yeah, then you just group your i's and your j's. And just like before, you set them equal to each other. So you have a dx equals negative 384 plus 9.4 alpha bd plus 61.2. And you have 0 equals negative 665.6 plus 3.4 alpha bd minus 22.2. And then you can solve for these and you have your acceleration. You guys feel good about this one? So the next one is almost exactly identical. So if you guys want, since these problems do take a long time, I can go over ones you guys have had specific problems on and try and skim over the identical ones. So, and also this is pretty much the basic procedure for any problem in chapter 15. So if you go back, like, draw your diagram, figure out your geometry and distances, figure out your constraints and what you're given, and then jump point to point to point with the velocities and accelerations. That's going to be every problem in chapter 15. You just have to be really careful with the cross products, positive signs, negative signs, and directions. Those are what's going to trip you up.
Can you go over that diagram?
The diagram?
I use the cosine.
Okay. So this angle right here is 60 degrees. So pretty much what I said was, bar AB, and this is 60 degrees. So this distance here is going to be AB cosine 60 degrees, and this distance here is going to be AB sine 60 degrees. Just like splitting a force up into its component vectors, it's kind of the same thing. So, does that make more sense?
So when we do R, D, relative to A, that's going to be sine.
So this is your y and x. So this is going to be in the I direction, and this is in the j direction. So that's why here for R with B with respect to A, 3 cosine 60 I, 3 sine 60 j, horizontal and vertical. Yeah.
The velocity and acceleration are negative concealed and it's a fixed point.
Exactly. It's pinned here, it can't accelerate. The bar itself can't go anywhere. Even though it has angular, the bar itself can't move.
And then at D, you said there's a acceleration only in the x and not the y.
Yes. The color here, because of the color can only slide along that pin. It's never going to move up or down. So you know the acceleration and velocity of the line is never going to be there. So, it's fine. And yeah, each problem will have its unique things like that. For 131, you have two ends that are fixed. You know the velocity and the acceleration of both of those ends. For problem 248, you have similar to this. You have one point that's fixed and one point that can only move in the y direction. Problem 257, you have a point that's fixed, and that one's a little bit trickier because you have a collar that can slide, but it slides at an angle. So it's never going to vary from that angle. So you can use that. And 258 is the exact same thing. So that's Does anyone else need this page still? Okay. Alright, so 257. You have pin joint next to bar. Alright, I'm making myself up for them. Alright, we'll make this bigger. And this is on the collar. And we know that this angle here is 25 degrees. And we know this height. And we know this length is 160 millimeters. Okay. So we have this. And again, the most important thing are the constraints. So let's figure out what the constraints are. So look at your ends. That's usually where they're going to be. So here at A, there's a pin joint. So you know that the velocity at A is going to be 0. The acceleration at A is going to be 0. And then at the other end, there's no constraints at B, because it's free to move, free to rotate. At D, you have a unique constraint, because it's only going to move that direction. But, since you know this angle, you can figure out what's going on there. So you can say it, well, if D, we'll call the position of D R. If RD in the x direction is going to change a certain way with the direction D in the y direction, this angle, think Pythagorean theorem. So you have this triangle, and this is in the x, this is in the y. So the tangent, opposite over adjacent, is always going to be 25 degrees. So I should flip this. So we have so this is from using trig. But then this also means that the velocity of D in the y direction and the velocity of D in the x direction is going to be the same thing, just taking the derivative of this. So these are your constraints. Constraints of each end. And then the problem tells you that it has an angular bar AB, or crank AB, we call it, has a constant angular velocity of 1.5 radians per second counterclockwise. Again, counterclockwise means positive, so you can just write this as 1.5 radians per second. You want to make this into a vector? Just like that. That's your omega AB. And then since that's constant, it follows that angular acceleration of AB is going to be 0. So bar AB has no angular acceleration. So yeah, this is the most important part of the problem, is this setup. Making sure you know what your constraints are and how to use them. So you guys feel comfortable with that? Feel comfortable figuring out what to do with constraints you're given? Okay. From there, is it okay if I go ahead? From there, you solve it just like the last one. Start it where you know and jump to the points you don't know. So just like before, we're going to go from A to B to start off with. Again, before we said this is 0. And like before, we know that this, from before, this is 1.5 in the K direction, crossed with, now RVA, if you look at the problem, it's a vertical bar. So we don't have to worry about the I direction. We can just say cross 40 millimeters in the J direction. When you're doing this, instead of converting to meters per second, save yourself some time and hassle and just work in millimeters and convert if you have to later when you're done with everything, all the calculations. It'll save you time and hassle and nasty decimal points. So usually working with the units you're given is the best way to go. Alright, if you do this, you get negative 60I meters per second. So that's our velocity at B. From there we can calculate the velocity at D. So you have, there's two ways of doing this. You can use the same equation as this one, or what you can do, so then you have VD equals VB plus omega VD cross R D with respect to D. The hard part about this is, there's two unknowns here, because you don't know I or J. You just know how they relate. So you can solve it. You have the third equation that you can solve that with. You also don't know this. And this is going to be in the K direction. So that makes things a bit easier. So you have three unknowns, and you do have three equations. But you could also just say, well, no, I guess that's the easier way to do it. We'll just leave it with this. Go with the easier way, not going to confuse you guys. Okay. If that's okay with everybody. Okay, we're just going to stick with this. So then, you have VDXI plus VDYJ equals negative 60I plus omega dB cross, and RDB, again, it's a straight bar, makes life easy on us, 160I. So this side's going to be 60I, K cross I is J, plus, this is a 60, 160 omega dB J. Okay, so then if we split this up into X and Y, or I and J, however you prefer to look at it, then VDX equals negative 60I, or negative 60 rather, here VI. Which is really convenient. Is this a value? And VDY equals 160 omega dB. So we have this one's good to go. This one we have one equation, two unknowns. So that's where we go back to the constraint we had before where we said VDY over VDX equals tangent 25 degrees. Well, you know this, and this you can solve, so then you can find VDY. Or what you can do is straight substitute this into there. So when you solve it, if you just substitute, you can say 160 omega dB equals, if you multiply this, bring this over here, v dx times the tangent of 25 degrees. And then, since we know this, plug this into here, radians per second. And again, that's just plugging and chugging, just algebra. And you just gotta make sure you're consistent and careful with your directions and with your units. Directions, pluses and minuses, they'll kill you. Always go back and double check all of them. Alright, so then once we have this, we plug this back into here, and we get v dy equals, I don't know where I wrote it down. You don't need it. I didn't write it down, but you don't need it. Okay. So this is actually one of the things we were solving for. So we were solving for omega vd. So okay. So once you have that, then what they ask for is the velocity of the collar. And again, you could just plug this back into here, find v dy, and rectify it. Which, honestly, works the best. It's how you have to do it anyways. The other way, like, you can write the equation and just say, well, this is just vd. So you have your vd vector, and write it out as a vector. But usually how he wants it is direction and magnitude, not as a vector. So we're going to go ahead and write that out as a vector. Write it out as a vector and then rectify it to direction and magnitude. So if you plug this back in here, you get v dy is equal to 28j. Okay, so now we have our vdx and our vdy. If we have that, then we can say the magnitude of vd is then the square root of the sum of each part, right? So the square root of 28 squared plus the square root of negative 60 squared. And again, all of these units are in millimeters per second. Very, very important. And so this will end up giving us 66.2 millimeters per second. Okay, so now that we have that, we need a direction. You can go the easy route and say, oh, my collar was in that plane. Like, it can only go at an angle of 25 degrees with respect to the x-axis. You guys, that's perfectly legitimate to say. Otherwise, if you take the inverse tangent of your y component divided by your x component, it should give you the exact same thing, because that's where we got it from before. You don't need to do this step, because it was stated in the problem that it's constrained to that 25 degrees.
Can I just use the vectors?
Pardon?
Can I just use the vectors?
The vector?
The vector is just show the velocity and
It is. Usually, at least when I took his course, he expressed to us that he preferred this way, and most of the time when he writes a result, he'll do it this way. So either way, technically is right. I would recommend doing it this way. So that's how it was always done for us in class. But technically, yes, the velocity is described by the vector. So. Okay, do you guys feel okay with that? And then for the acceleration, which is problem 258, all you do is the exact same thing, only with the acceleration equations except for the velocity ones. So, that should. Are you guys feel confident with chapter 15? Are there any more problems in chapter 15 you want me to go over? Alright. How about chapter that it's sliding, and it gives you your mu k. So you know that there's a friction force, and it's going to be sliding this way. So you have a friction force here, and a friction force here. You also have two normal forces. You have a normal force in the back, and you have a normal force in the front. Now, ideal conditions, this is just kind of chilling, sliding on the ground, and these are both equal, and it's the weight divided by 2. Oh, and you also have the weight. But this isn't asking about ideal conditions. So, what it is asking for is the acceleration of the cabinet and the range of values of this height for which the cabinet will rotate. But before we start, let's go ahead and just do our kinetics, just do our sum of the forces, statics. So for all the all the chapter 16 problems, the sum of the forces and sum of the moments are important. So starting off with that, let's do that. And we'll try to coordinate system too, just really quick things. Alright. So your sum of the forces in the x direction is going to be 100 newtons. Oh, and these are two separate forces of friction. Back and front. Minus the force of friction in the back. Minus the force of friction in the front. And this is going to be equal to the mass times the acceleration in the x direction of this bar. Alright. And these are going to be equal to 100 newtons minus, and since the friction force is just mu sub k times the normal force, we'll just go ahead and write it that way, mu sub k and v minus mu sub k and f. Alright. So we have that. Now we can do the sum of forces in the y direction. And say that the weight minus the normal force in the back, negative the weight plus the normal force in the back plus the normal force in the front is going to be equal to 0. And the reason it's equal to 0 is because it's constrained here. It is not going to go up or down without an up or down force applied to it. It's just not. So we don't have to worry about that. That makes things easier. And this is equal to m times the acceleration in the y direction. So we know that this acceleration is 0. Makes life a lot easier. Alright. And then we have the sum of the moments. And we're going to take it about the center of gravity. So this is the part where the geometry is really important. So you need to know the distance each of these are from the center of gravity. Pretty much all you have to do is split the difference. It's going to be 0.3 meters here, 0.3 meters here. And this height, well, we don't know. That's the hard part. But we do know that this force, the distance between this force and the center of gravity is 0.9 meters minus whatever this h is. Just from the geometry. And later on we'll be solving for this h. So, from there we take some moments and say, and starting here, we'll start with this force. Go in there, it's going to be negative. Using your right hand rule. Right hand rule is also very helpful. Then you have negative 0.3 times whatever this force is. And then it's going to be plus 0.3 times the normal force of the front wheel. Plus 100 newtons times whatever this distance is, which we said was 0.9 minus h. And then we've had the friction forces too. You have to get the friction forces. times your angular acceleration. And again, on the equation sheet, there's this box here that's got plane motion of a rigid body, and that's where all of these equations are from. That's really, really, really what you need. It says sum of the forces in the x is equal to mass times the acceleration in the x direction. So the forces of the y equal to mass times the acceleration in the y direction. And sum of the moments about the center of gravity is equal to the moment of inertia times the angular acceleration. Okay. So this is asking for the acceleration in the x direction. So then we're going to be using these two equations. These two equations combine to help us. So I'm going to go ahead and go to a different page. Is everyone good with this? So then the equation we had before were that mass times the acceleration in the x direction is equal to 100 newtons minus mu sub k times the normal force of E in the back minus mu sub k times the normal force in the front. Alright. So this is great except for the fact that we have one equation, three unknowns. Solving for this, we don't know this, or that. But the problem does give us the mass. So the mass is 20 kilograms. We know that. We're good there. But we have another equation that'll help us a lot. So the second equation, so the forces in the y, said that normal force B in the back plus the normal force in the front is equal to the weight. Once you rearrange it. So then, if we rewrite this equation, we can say 100 newtons minus mu sub k, factoring out a negative mu sub k, nb plus nf equals mass times the acceleration in the x direction. Okay. So, we say that this is the weight, which is equal to the mass times the acceleration due to gravity. And then we have everything we need. We can solve for ax. We can say ax equals 1 over the mass times, and we can just go ahead and I'll write it out in the 30 numbers. 100 newtons minus mu sub k mg. Does everyone see where that came from? Everyone good with that? Okay, so then plugging in numbers, we have 1 over 20 kilograms times 100 newtons minus mu sub k is 0.25. Our mass is 20 kilograms. Acceleration due to gravity, 9.81 meters per second squared. And this is going to give us an acceleration equal to 2.55 meters per second squared. And so this acceleration here, since we already said the acceleration in the y was going to be 0, we can say that this is the acceleration of our cabinet. So this is part A. Alright, so we all agree? Alright. So the next part is where we're going to use our last equation. Go ahead and so we want to know how the cabinet won't tip. If the cabinet's not going to tip, that means your angular acceleration is going to be 0. So that takes our last equation, which was negative K NB minus 0.9 UK NF equals I alpha. So this is exactly what we had before. This was our sum of the moments about the center of gravity. And pretty much we just said that this term is 0. Okay. So now we have all of this. And some of it can be simplified like we had before. But the most, yeah. So we can go ahead and simplify some of it. Or expand it, I suppose. Actually, let's just stick to the obvious for right now. Okay. So we have this equation. And now it wants a range. So range means that there's a max and a min. So we have to know what the max height's going to be and what the minimum height's going to be. So the maximum height is going to be when it's just about to tip over. And like if you tip it anymore, then it's gone. So that's going to be where that front wheel has all of the force applied to it. That's when the back wheel is coming off the ground. So that's when you can say your max is at the normal force in the front is equal to the weight. And yeah. I have no idea what's going on. I tried getting, like I just used the link in my email.
Did it work at home?
Yeah, my computer was. Sorry. Oh. So this is going to be your condition for maximum height. Now the inverse is true. At the minimum height, it will tip backwards if all the weight's coming off of the front wheel and onto the back wheel. So then, your minimum is going to be when the normal force at the front is 0. And you could do the exact opposite thing. You could say your max is when the normal force at the back is 0, and then the normal force and your min is when the normal force at the back is the weight. It works either way. Because remember, you also have the equation that normal force at the back plus the normal force at the front is equal to your weight. So that's going to be the equation that you use. So this equation and this equation. So let's look and see what our notes are. So here, once we say that normal force is equal to the weight, we can say that normal force at the back is equal to 0. It knocks out this term, and knocks out this term. And then we know this, we know this, we know this. And so then for your maximum condition, you have 0.3 times the weight plus 100 times 0.9 minus h minus 0.9 mu sub k normal force of the front, which we said was the weight, equals 0. And then your weight is just your mass times gravity. So then it's just algebra. So this condition leads to this. And then when you do the algebra, you get h is equal to 1.047 meters. So you want me to go through the algebra, I guess? You okay with that? Okay. So then you have to deal with your minimum condition.
One more time.
Yeah. Well. Okay, so that's our maximum condition. So then going back to our minimum condition, we're saying that the normal force in the front is 0, which means that the normal force in the back is the weight. So it's kind of like exactly the opposite of this. We'll have this term, but not this one. We'll have this term, and we'll have this term, but not this one. So it's kind of like exactly the opposite. So then for your min, you have 0.3 times the normal force in the back, which we said was the weight, 0.3 times the weight, plus 100 times 0.9 minus h. Oh, sorry, negative 0.3 times the weight. That makes a really big difference. Minus 0.9 use of k times the weight equals 0. And again, we can solve for h. And here, h comes out to be negative 5.43 meters. Okay, and before you write down on the exam that your range from h is negative 5.43 is less than or equal to h is less than or equal to 1.047 meters, this isn't going to happen. The box doesn't exist there. So you don't even have to worry about this. You can just say that h is going to be less than 1.047 meters. So does this make sense how I got all of this? Everything follows? Yeah, and we go over 77, or 85, whichever you guys prefer. Like, can we just start with 85 and then 87 and go over that? We can do both. Alright, sounds good. Okay. So for problem 77, we have a hanging bar. We have, of course, alright. Yeah. 77. Okay, so then from this, we have three forces. You have your force here, P. You have a reaction at x and at a in the y direction, and a reaction at a in the x direction. Does it matter which way you draw those? Not a bit. I probably just made life a little bit more difficult for myself by putting this negative, so I'm going to go ahead and put this positive. Pretty much, if you draw it the wrong direction, you get a negative number. Definitely not the end of the world. So. Alright. So then let's do the sum of the forces. The sum of the forces in the x is going to be ax minus p. Which is going to be mass times the acceleration in this direction. Okay. Oh, sorry. There's also weight to take into account. Okay. Alright. So then we have the sum of forces in the y. And that's going to be AY minus W. That's going to be the mass times the acceleration in the y direction. And like before, I think we can all agree that this rod is not going anywhere in the y direction. Fixed in 0. That's great. Okay. So then, some moments about G. Is going to be, this is where you can either use numbers or variables, and variables will probably make your life a little bit easier. Even though it looks a bit more confusing, so bear with me a little bit. Okay. So, some of the moments of G, AY, and W not going to be taken into account. So then we have P and AX. So, for this we have negative L over 2 times AX minus, we don't know what this distance is. I don't think it gives it to us. Oh, it says at h equal, no, we're solving for the distance h. So we don't know what h is. And it's minus whatever that distance is. So if this is L over 2, this is going to be h minus L over 2. And that's times b. And this is going to be here I bar times alpha. Alright, so we have our equations. So, just a sec. I have to control all of this. Okay. We have our 3 equations. Yes, this is so where I got that was because the center of gravity is at L over 2 and our P is at H, so then this is just going to be H minus L over 2. So is everyone with that? Okay. So we're solving for this distance H, for which the horizontal component of the reaction at A is 0. Great, we have 3 equations that we can knock stuff out of. 0, 0. In the problem, it says we're finding the distance h for which the horizontal component of the reaction at A is 0. So, yeah, pretty much this is 0. Okay. So once we knock that out of the picture, then we have a few things that work to our advantage. The important thing for this problem, since this never gets knocked out since we're solving for it, we have to know what this is. So, for this rod, the moment of inertia is 1/12 m. I don't know if this is on your equation sheet. I don't think it is. I think, yeah, you just have to know that. For a rectangular bar, this is the moment of inertia. Good thing to have memorized. Okay. So then, for part A, we're solving for h. We want to know this height. So we're going to use this equation here. It's got height in it. Okay. So then we have negative h plus equals 1/12 ml squared alpha. I think you have to do problem 76 to be able to get this, perhaps. Because you need to know the... Just say. Okay. So what you have to do to solve this is solve part B first. Confusing? Yes. That's why I was confused for a second. It's okay to be confused. If you can't solve the first part, go to the second part. Hard part is, we know this, we know this length, we know this, we know the mass, we know this length. We don't know this, we don't know this. Part B asks us to solve for that. So, let's try part B first. And that might happen on the exam. You might look at it and say, like, well, this is how I want to solve this, but I need something that I get in the second part of the problem. Perfectly acceptable. Skip it, go to the second part of the problem if you can. Okay. So now we're going to do like we were doing for the chapter 15 stuff. We know that our acceleration at A is equal to 0. We know that our acceleration at the center of gravity is what we're looking for. Because our acceleration at the center of gravity is going to tell us our angular acceleration of the bar. So that's another little trick to this problem. This alpha, the alpha of the bar, is that you can find it at the center of gravity. You can go to B as well, but you don't know any information. You know information at the center of gravity. So go to the center of gravity. Okay. So then we use the same equation as before. Acceleration at G is equal to acceleration at A plus, which we already said was 0, alpha, which is going to be in the k direction, cross r with respect to A, plus omega k cross omega k cross r with respect to A. The convenient part of this is that initially you can say it's not going anywhere. It says the force is applied. If it's not going anywhere, velocity, 0. It's about to go somewhere, it's not going somewhere. So, that just pretty much simplifies our life down to acceleration, bar, center of gravity. Sorry, I didn't mention that before, but that's an important thing to know. This bar means at the center of gravity. Acceleration of gravity at I plus acceleration of gravity, center of J direction is going to be equal to this alpha in the K direction cross, and G with respect to A, go ahead and go back one real quick. R of G with respect to A is right here. It's this L over 2, downward in the J direction. So that's what we're going to plug in. So then this is going to be cross negative L over 2J. Everyone see where we get that? Okay. And we already said that the acceleration in the y was 0. And actually, if you do the math, that's going to prove it. So we'll just go ahead and show them it's 0. So we have AXI plus AYJ equals, and this K cross J is negative I, this will be L over 2 alpha I. If you look at our I's, you can say that AX equals L over 2 alpha. If you look at the J's, you can say that AY equals 0. So that confirms what we said before. Acceleration in the y direction is going to be Now this and this, we don't know. So that's why we have to go back and look at this equation here. So this equation here, since the horizontal component of the force of A is 0, we can say that AX equals negative whatever this force is divided by the mass of the bar. Everyone good with that? Just back to the sum of the forces. Okay. So, then we can say that negative P over M equals L over 2 alpha. Since alpha equals negative 2P over the length of the bar times the mass of the bar. I know it's a lot of confusing, like connecting the dots between equations. But just keep track of what you know and what you don't know, or what you have and what you don't have. Keep track of that while you go along. That's going to be a lot easier to put those pieces together. It's kind of like doing a puzzle with output and diagrams. Okay. So this is part B. And if you plug numbers in, and be careful because you're given the weight in the problem and not the mass. The weight is just mass times gravity, so all you have to do to get mass is just weight divided by gravity. But if you forget that, you're going to get wrong answers and wrong units. So never, never, never forget to double check if you're given a weight or a mass and to plug in the right one. Okay. So when you plug in the numbers here, which you're given, P is 1.5 pounds, your length is 36 inches, and your mass is going to be 4 pounds divided by 32.2 feet per second squared. Again, another caution point. Inches, feet. Save yourself. Call this 3 feet. Always, always, always go through, make sure your units line up. Like, that's just as important as the negative signs. It'll keep you from making mistakes if you just go through and double check those things as you go. Alright, so when you plug all the numbers in, you get alpha is equal to negative 8.087 radians per second, which means it's 8.07 radians per second, and it's going to be clockwise. Oh, sorry, radians per second squared. That's the easiest thing. Okay. So does everyone see where we did this? Everyone good on this? Then we're going to go back to where we were before when we tried to do part A. We didn't know this value. Now we know it. Great. So this is going to be an unknown to a known. Now we have one equation and one unknown. So we can say negative hp equals 1/12 ml squared alpha minus L over 2 times P, which means H equals L over 2 minus 1 over 12 times P M L squared alpha. Everyone agree? Okay. So then you plug in numbers and you get 3 feet. We'll just work in feet because it's easier. Minus 1 over 12 times 1.5 times 4 pounds divided by 32.2 feet per second squared. Again, double checking because this is mass, not weight. Gotta do that again. Times 3 feet squared. And again, negative. Clockwise, negative. And this will give us a height of 2 feet, and if you want it in inches, 24 inches. Is everyone okay with this problem? We want to see how we got everything. Feel like you can do it on an exam? Hopefully. So yeah, start off some of the moments, and then see what equations you have, see what your knowns and unknowns are, what you can solve for. So, you guys want me to go through 85 also? Yeah. Okay. Now this one can be a little bit confusing too. So center of gravity at L divided by 2. Alright, so a uniform rod of length L and mass M is supported as shown. If the cable attached to NB suddenly breaks. That suddenly breaks is wonderful and helpful. Suddenly breaks means that this is no longer there. So before, where you would have had a force, and it would have been kind of like pinned there, now there's just nothing there. So then, when you're figuring out where your reactions are, where your forces are, you have a bit of a break. Because now, there's no reaction force there. You have the weight here, and reaction forces here. But there's now nothing there. It's just like it's a bar. It just kind of started there and is going to stop somewhere else. So, that makes things a little bit easy on you. Alright, the other thing that makes it easy on you is this bar right now is perfectly horizontal. Since this bar is pinned and it's perfectly horizontal, it's going to be very difficult for this bar to ever move anywhere in the horizontal, right? In the vertical, however, it can move. It's free to rotate, so that it can move to vertical. At this instant, only at this instant. So that makes it easy for you to say is like, well, I know at G, the acceleration in X is going to be 0. It's not going to. And again, that's just kind of like a little trick. But it makes it easier when you do like some of the forces. So let's start in the X direction. Let's do some of the forces in the X direction. We have Cs equals mass times the acceleration at X, which we all just agreed was 0. So we have 0. Alright. Now we have the sum of the forces in the Y. And that's going to be your reaction at C in the Y minus your weight equals mass times the acceleration of G in the Y direction. And we all agree it can move in the Y. It has the freedom to go up and down because of the rotate. So that's just how it is. We can't cancel anything out. Alright, now there's some of the moments about the center of gravity. That's going to be length from here to here, which this is L over 4, this is L over 2. This is going to be L over 4. So we have negative L over 4 times Cy. And then, since this is acting at the center of gravity, and this is 0, that's all you have to worry about. It can be I bar times alpha. Does everyone see that? Okay. So then, let's look at what we're solving for. We're solving for the acceleration of NB and the reaction at the pin support. Okay. So we need to know both of those things. Well, let's see what we have to work with. See what our nodes are. We know this reaction. We don't know this reaction. Our weight, this is all in variables again, so it's going to be kind of, different to solve. You can't just plug numbers in. We know weight is equal to mass times gravity, and we're given mass, and we know gravity. So you can say that we know this, and we know this, and we remembered that I bar for a beam is going to be 1/12 ml squared. So we know this. Which leaves us with 3 unknowns. We don't know Cy, we don't know Ay, we don't know alpha. So we have to solve for all those things. So how do we do that? We do like what we did in chapter 15. We go from where we know to a point where we don't know, and we solve. So let's go from 2 points where we know. We know stuff at the center of gravity, and we know a little bit about, we know about C, we know a little bit about the center of gravity. So let's go ahead and solve for the acceleration at the center of gravity. Usually for all of these problems, solving for the acceleration at the center of gravity, you want to do it. It gives you a lot of information. It's really helpful, and you need to solve problems. So we know that the acceleration at C is 0. Pinned, constrained, not going anywhere. So then the acceleration at G is going to be the acceleration at C, which is 0, plus alpha of the bar, k, cross r of G with respect to C, plus omega k cross omega k cross r G with respect to C. And again, this says that the cable suddenly breaks. At the instant we're looking at, this bar isn't going anywhere. So the velocity is 0. So just like the last problem, it makes our lives a lot simpler, which is good. So we can say that AXI, and remember from before we said that since it can't move in the x direction, this is 0 also, plus A bar yj is equal to alpha, which we don't know, in the k direction, cross with rg with respect to c, was length over 4 in the I direction. So this is just L over 4 I. So then we can say A bar y j equals k cross I is j, L over 4 alpha j. Solve for this, and we can say our alpha is 4 A bar y over L. Now from before we had the equation that Cy minus mg equals MAY. This was our sum of the forces in the y. So we don't know this or this, but we can solve for this. We can solve for A bar y by using this equation. So then we can say A bar y is Cy over M minus g. You guys all see where that came from? Good with that? Okay. And if we have that, we can say that this is equal to 4 over L at Cy over M minus G. So now we can use this. And we can plug it back into the equation we had before, which said that, let's go back to it. L over 4 Cy equals I alpha. So let's go ahead and copy that down over here and start plugging in some variables. So we have negative Cy over 4 Cy times L over 4 equals I bar alpha, means negative Cy over 4 equals 1/12 m L squared times this, times 4 over L times Cy divided by M minus G. This cancels. And so pretty much from here, it's algebra to solve for that other reaction. So we solved, one of the things we need to solve for, well, in order to get anything, we need to solve for this angular acceleration. So that's the first step. So now that we have that, it's a bunch of algebra. Do you guys want me to go through the steps of the algebra, or are you guys just okay with me writing down the solution? Okay. So then when you go through all the algebra, and you plug in some numbers that you know, because you know, yeah, pretty much a lot of stuff cancels out. That'll just be the way it is, because you have fours, everything else, it cancels out pretty nicely. So you end up with this Cy equals 0.57 times mg. And it's going, since it comes out positive, it's going to be in the positive x direction. This right here is just 4/7. That's what it comes out to if you don't reduce the fraction to a decimal. Either way is acceptable. So, yeah, if you just crunch through the algebra, that's what you're going to end up with for Cy. So now that you have that, the other thing it asks for is the reaction. It just asks for the reaction of the support. Oh, this is actually part B. My bad, sorry. Again, we don't have to solve in order. I apparently never do. So, this is part B. This is the reaction of the pin support, because we already had that Cx is 0. Alright, so then the other part is the acceleration of end B. So the acceleration of end B, we can just say, well, we know the acceleration at C, and we know the angular acceleration, so we can find the acceleration at B using the same equation as before. So the acceleration at B equals the acceleration at C plus alpha k cross r of B with respect to C plus omega k cross omega k cross r B with respect to C. Just like before, not going anywhere, 0. Just like before, it's pinned, this is 0. So then what we're left with is the acceleration at B is going to be our alpha, which we solved for before. And again, if you go through the way we had it before and plug in numbers and try and reduce what you can based on knowing gravity, it ends up being negative 1.5 RBC. If we go back to our picture, since this is L over 4, this is 3L over 4. So we just say 3L over 4 in the I direction. So this is going to be cross 3L over 4I. Alright, so then, like, this is as simple as it is. We just did the algebra reduce. And we come up with K cross I is positive J. The L's are going to cancel out. And your acceleration B is going to be 1.287 times the acceleration due to gravity. It comes out to be negative, so downward. Does everyone see how I did that? Does everyone feel comfortable with this, know where everything came from? Does everyone think they could repeat it if they needed to? Maybe after a bit more studying? Oh, we still have a bit left. If there's any other questions you guys have, questions in general, questions over the stuff we didn't go over in chapter 15. It'll probably make it easier on you to change to revolutions per second. But again, that's revolutions per minute, so you're going to want to change it to radians per second. Right, because, well, that'll give you revolutions per second. But remember, there's 2 pi radians per revolution. RPM is revolutions, not radians. Okay. Freshy. Alright. So you have 45 RPM, so that's 45 revolutions per minute. So yeah, like you said, you can multiply that by 1 minute per 60 seconds. And then it's just another ratio. There's 2 pi radians per revolution. So then minutes cancels and revolutions cancel. So you multiply by 2 pi and divide by 60. So you'll definitely want it in radians. Are there other questions you guys have? Anything else you guys want me to go over? Everyone good? If you guys saw the assignment sheet